Good afternoon, everyone. I'm Ziqiao, and I'm presenting our work on non-blind deblurring for fluorescence, a deformable latent space approach with kernel parameterization. This is a collaboration between Stony Brook University and Brookhaven National Lab. In this paper, we are solving a non-blind deblurring problem for ptychography fluorescence. NBD means the blurring kernel is known during deblurring, and Ptycho-FI can benefit from NBD because ptychography can solve the kernel. Then we can use a larger kernel for fluorescence and do NBD, and the acquisition is much faster because of the large kernel. The key challenge in this work is how to generalize the deblurrer to diverse blurring kernels. If we use an encoder-decoder network to learn deblurring for a fixed kernel, it learns the latent space of images from this blurring kernel, and the images from other kernels are not in this latent space. In Ptycho-FI, we know the kernel and we want to properly use it. We want to use the kernel to directly parameterize the deblurrer and dictate how we restore the image. We propose a neural network to learn the deformable latent space to address this challenge for NBD. We propose to train this deformable latent space in two stages. At the first stage, we use images from one fixed blurring kernel to train a deblurring encoder-decoder. This establishes the standard latent space. At the second stage, we freeze the encoder and decoder and train the deformer portion of the network. In the learning batch, there is one clean image and multiple blurred images with different kernels. The objective is to deform the non-standard latent space vectors to fit in the standard space. The deformer is parameterized by the parameters of the kernel K, for example, the focal distance and pixel size. The parameterization of the deformer network is implemented via using dynamic convolutions everywhere. This is like a linear combination of standard 2D convolutions. In 2D convol, we normally take a filter K to convolve with a tensor H. For dynamic convolution, we have a group of n sub b such filters of K sub b to do convolutions, and then dot convolve the tensors with a vector W. W is computed from the parameter input through a few learnable layers. This is like a basis transform with n sub b convolutions as the basis and the vector W as basis coefficients. The advantage of using dynamic convolution is that parameter control over the transforms is covering all the layers, which offers great flexibility to adapt to the NBD. Also, all these layers have transforms from the input parameter theta of K to the basis coefficient W. We can choose to have them all separate or share weights to preserve information across the layers. In our experiments, we tie the weights within each residual block, shown here, in 2-layer and 3-layer groups to share info. Now I'm going to show some experiment results. This is a deblurring comparison of no deform, simple deform, and our method. No deform does not consider the changing kernel. Simple deform has a very simple interaction with the parameters. The results show that parametric models win, and our method is better than simple deform. In this figure, we show NBD comparison with a few other methods. Our method shows better quality and less rippling artifacts compared to others. In this figure, we show NBD comparison on fluorescence images. We show that our method is among the best and is also fast to compute because we do deformation in the low-dimensional latent space and the model is lighter. In conclusion, we presented a parameterized non-blind deblurring method using deformable latent space, which accounts for the kernel change head-on. This method improves Ptycho-FI quality and makes higher throughput possible. Please visit our poster for more results. Thank you for your attention.